Alright, so this is a scholarship physics tip looking at energy in simple harmonic motion. So first, let's start off with our basic simple harmonic motion spring mass system, right? And this is obviously a horizontal spring mass system, right? So this is a mass, and obviously, as we know, if we stretch that mass, so we pull it this way, the system is going to gain elastic potential energy, and therefore when we release it, it's going to oscillate in simple harmonic motion in between gaining potential energy and then converting that into kinetic energy, and then back to potential energy, and then back to kinetic energy, and so on, right? And so just going through the basic understanding of this, we obviously know that right over here, this is our equilibrium position, right, EQ, and so this is obviously the unstretched length, right, unstretched length of the spring. So if we were to pull the mass, let's say this distance right here, so we the box now looks like this, okay? Here is our mass now. And we can call this distance B, okay? And then as I stated before, if we were to release the mass at this position, it will gain kinetic energy and move back to the equilibrium, and also move past the equilibrium, gain some potential energy again, and then keep oscillating back and forth, okay? If we were to analyze the energy changes in the system, let's say when we pull it to distance B, we can say that this is the initial energy of the system, and then when it arrives back at the equilibrium position, we can say that this is E final, okay? The reason why we use E final as the equilibrium position rather than when the mass is over here, this is because the energy at this point is the exact same energy at this point, right? These 2 points both have elastic potential energy. It's just in this case, the spring is compressed. However, in this case, the spring is extended. But theoretically, the amount that the spring has displaced on both sides, so that x value should be roughly the same, and so the elastic potential energy would be the same. And so as we know, E is equal to half kx squared. If x is 0, that means our potential energy at the equilibrium position will be 0. And so if we stretch the mass distance B and then release, we know our initial energy is going to be equal to our final energy, right? And our initial energy is half k b squared, right, not x, because we have stretched it at distance b. X is just a common variable that's used for displacement. And finally, this is all going to be equal to the kinetic energy of the mass, because as the mass moves this way, obviously once it reaches equilibrium position, like I said before, there's going to be no elastic potential energy, and so the only energy that is present is the movement, and so we know that's kinetic energy. And so we get this nice relationship as so. And so like I said, this is just going to oscillate back and forth. And so if we were to just graph this for a second, we have our energy on this axis, right? And then we can have our elastic potential energy, and our kinetic energy is going to follow the opposite relationship to that, right? So we should know this from our regular NCA. Now, the main question that I want to propose for this video is, does this relationship, when I mean this relationship, I mean this relationship right here. So does this relationship hold when we consider a vertical spring mass system? Okay, so obviously on this scenario, we have considered a horizontal spring mass system, but if we were to do a vertical spring mass system, like so, does this relationship still hold? If you want for good practice, you can try it yourself and see if you get the answer correct, but nonetheless, I will go through it for you. Okay, so the first thing I want to say is that if we have a spring just hanging from the ceiling, no mass attached to it, it's going to have a unstretched length, okay? So we can call this line the unstretched spring position. And this spring obviously has a spring constant K, okay? And so now let's take this exact same spring and now let's add a mass onto it. Okay, let's like so. There we go. And so obviously when we add a mass, we add a force, right? Because of the weight force of the mass, and therefore due to F is equal to kx, if we add a force, there's obviously going to be a displacement present. And so obviously we can call this mass m, and let's say this spring has displaced a distance of a. okay? And we can call this position the equilibrium position, right? So that's the equilibrium. So this is the position where the spring is unstretched, and this is the position where the spring rests when we hang a mass on it. And just to reiterate, this is called the equilibrium position because the sum of forces on the mass is equal to 0. In other words, there is a force coming downwards, which is our weight force, right, mg, and that's equal to our kx, okay? However, in this case, x is not x is a, because that is what we call the displacement, so we can replace that, right? Mg is equal to Ka, right? So we can get rid of that, move that up there. And so I'm going to write this out as a is equal to mg all over k, and you'll see why I have done that later on, okay? But for now, we'll just leave that there. And so now, just like all our other simple harmonic motion mass systems, we need to displace the mass a little bit, right? So we can displace the mass like so, have a spring come down, let's say about there, okay? So we still have our mass, right? Again, these are the exact same mass. Obviously, I can't draw two drawings on top of each other because that would get messy, so I've just drawn them side to side. And so let's say this mass has now been displaced a distance b, okay? Right, and we can obviously draw out our line right there. And so, just like in our previous example where I stretched it also a distance b, this is our initial energy, and so I can call this our initial energy, right? Again, initial because that's when we are releasing the system, and that's when it starts its simple harmonic motion, okay? And again, just like in our horizontal scenario, our equilibrium position is going to be our final energy, right? So we can call this EF as well. Okay, and also, as this is max displacement, we can say that the height at this point is equal to 0. And because the height is equal to 0, the gravitational potential energy at this point is going to be 0, right? Because we know that EP is equal to mgh. So a common confusion you might have is how have we just set height to 0 and then therefore gravitational potential energy to 0? Well, obviously this question is a question of conservation of energy. And when we talk about conservation of energy, we are only interested in the changes in energy, right? And so just going off to the side here, let's say we have a person, okay? Timmy, let's call him, okay? And Timmy is 10 meters above the ground. Okay, let's say this is a solid platform. And then Timmy jumps, okay? And he has an insane vertical. So he jumps 4 meters into the air, right? If we are considering the energy changes of Timmy, right? Let's take his initial energy at the top, and then the final energy is the kinetic energy as he drops down. In this scenario, we can take into consideration the extra 10 meters that Timmy is off the ground, but that will just end up canceling out, right? So we can either take h is equal to 4 at this point, or we can take h is equal to 14, right? In this case, the equation is simple, right? We have our initial energy is equal to our final energy, and therefore our mgh is equal to half mv squared, where our h is equal to 4 meters. However, in this case, we had to do mgh is equal to half mv squared plus mgh, right? Now I should label this, let's say this is h2, and this is h1, where h1 is equal to 10 meters, and h2 is equal to 14 meters, okay? For all intents and purposes, these two equations are the same, like they are equivalent. Let's say, let's carry this out for a bit, okay? Let's park this for a second. You can skip ahead if you already understand this. But for those that don't, you can stick around. Let's say we're trying to find the velocity, okay? We want to find the velocity. Let's say Timmy has a mass of 50 kgs, okay? Let's carry out this calculation. So we know he has a mass of 50 kgs, and so we can rearrange for our velocity, and so we get 2 mgh all over our mass is equal to v, and we can square root that, right? And so we can cancel out our masses, and we get square root 2 gh, right? And we know g is 9.81, and his mass is, the height is 4 in this case, right? We defined this to be 4 meters, okay? And this gives us a value of 8.86 meters per second, okay? And let's do this scenario, okay? right? So we have mgh2 minus mgh1 is equal to half mv squared. Okay, so that means mg h2 minus h1 is equal to half mv squared. All right, so we can cancel out our masses on both sides and we get gh2 minus h1 is equal to half v squared. And therefore 2gh2 minus h1 is equal to v, and we can square root that. And therefore we can plug in our numbers. 2 times 9.81 times our h2, which we defined as 14, minus 10 is equal to our velocity, and therefore, simplifying this, we get 2 times 9.81 times 4 is equal to our velocity, and lo and behold, we have the exact same equation that we have up there. And so therefore, this is equal to 8.86 meters per second. So, bit of a tangent, bit of a slight tangent, but when we are considering energy conservation, we only want the relative changes in energy, right? So if we set this to 0, we're basically saying this is the minimum amount of kinetic energy that is ever going to be in the system, and therefore it's going to cancel out anyways, so we may as well just set it to 0 to make our life easier, because obviously this calculation was a whole lot easier than this calculation. And so now that we got everything defined, we can compare the energies initially to the finally, and we'll see if this relationship holds up. So energy initially is equal to our energy finally. Initially, we only have elastic potential energy, right? Because our mass is at rest. And obviously, we have discussed why gravitational potential energy is 0. And so we get half k times our distance. The distance that we have stretched is a plus b, right? So we get a plus b squared. And that's equal to our energy finally, where we have some elastic potential energy due to this distance a, okay? So we have half k a squared, right? Plus half mv squared, right? Because as we release the mass, it's going to move up this way, and once it reaches the equilibrium position, it's going to have some kinetic energy because it's moving, right? Plus mgb, right? So this is our gravitational potential energy equation. And obviously, if we take this height as 0, when the mass reaches up here, it's going to gain some gravitational potential energy, and the height it gains is distance b, okay? So now we can expand this out, and we get half k a squared plus 2ab plus b squared is equal to half k a squared plus half mv squared plus mgb. And now we can expand this out, and we get half ka squared plus kab, right? Because 2 times half is just 1, so we can just get rid of that. Plus half kb squared, and that's all equal to half ka squared plus half mv squared plus mgb. Right, so we can already see some things that we can cancel. So that would be our half ka squared. So we get kab plus half kb squared is equal to half mv squared plus mgb. Now, if you remember earlier, I said a is equal to mg all over k. And so we can make that substitution into there. And we get k is equal to mg all over k times b plus half kb squared is equal to half mv squared plus mgb. And obviously we can cancel out these k's, and we get mgb is equal to half kb squared, and that's all equal to half mv squared plus mgb. And what do you know? We can cancel out our mgb's. Oh, sorry, that shouldn't be an equal. That should be a plus. Right, sorry. And what do you know? We get half kb squared is equal to half mv squared. And lo and behold, the relationship still holds up, even in a vertical system. Just slightly more complicated to derive, but it's good to know that when you're in an exam situation, you know this relationship still holds, okay? And that'll be it.